Hi, and welcome to 4.3 Net Force, page 2. Number 8 says find the acceleration of a 2 kilogram block. So they're looking for the acceleration. They tell you what the mass is in the following diagram. Now, we'd like to use Newton's second law, but we don't know what the net force is. They tell us these two other forces. Remember, the net force is the sum of these two forces. So before we could use Newton's second law, we have to add these forces together. This one's 7 newtons to the left, so we make it negative, plus 3 newtons to the right. So therefore the net force would be negative 4 newtons, meaning the net force is 4 newtons to the left. As I said before, this is not an additional force that's being added to the block. It's the net force. It's the resultant of these two forces together. So you could either think of 7 newtons to the left and 3 newtons to the right, or just ignore these two and think, okay, 4 newtons to the left. That's the net force. And that's what we're going to do when we plug in to our formula here. So the acceleration is 4 newtons. The acceleration is equal to 4 newtons to the left, so we make it negative over 2 kilograms. So the acceleration is actually negative 2 meters per second squared. And again, the negative just means it's to the left. So acceleration is also a vector. Since we got a negative number when we did the calculation, it should mean that the acceleration is pointing in the negative direction, to the left. And that's true, because the net force is pointing to the left, and the net force always acts in the same direction as the acceleration. Okay, good. Number 9 says the block below is accelerating with a magnitude of 4 meters per second squared. What is the magnitude and direction of the net force acting on the block? And then what is the mass of the block? So they're going to be looking for the mass, but first they say, okay, what is the net force? Now this one's a little bit different because you have forces in the x direction and a force in the y direction. So you might want to break it up a little bit. Let's make the x direction blue. So let's say the net force in the x direction is equal to, so now we'll ignore 6 for now. Let's just sum up what's in the x direction first. 10 newtons to the left is negative 10, plus 10 newtons to the right, we make that positive 10. So the net force in the x direction is actually 0 newtons. In the y direction, you only have one force. The net force in the y direction is just 6 newtons plus nothing else. There's no other forces in the y direction. So if we wanted to do a vector sum, kind of like we did on number 3 on the previous page, where we had to do like Pythagorean theorem and everything like that, we could do that at this point. But luckily, since the net force in the x direction is 0, we add 0 plus 6, the net force is just 6 newtons south. And some of you might have been able to tell right away, okay, these two are balanced, I got 6 newtons south, that's what the net force must be, and you'd be correct by looking at the diagram. So this is 6 newtons, and we can make it negative because it's going downwards. Okay, and also by looking at this diagram and looking at the direction of the net force, we should also make the acceleration negative. Now, in the problem, it doesn't appear that, oh, they made a mistake. But remember, it says the magnitude of the acceleration is 4 meters per second squared. They're not giving the direction on purpose. They're like, okay, you figure out what direction it has to go. We'll just give you the magnitude. And since we know the net force is going down, the acceleration must also be going down. Again, you could just kind of figure that out by looking at the diagram. And this is important because when we do the calculation, and we're looking for the mass, part B, so this is for A, now we could start part B. We know our given information, and we could just plug into the formula. And it's kind of nice how it works out, because if you make your signs correct, this is negative 6 newtons, we're looking for the mass, this is actually negative 4 meters per second squared, you get negative 6 divided by negative 4, which would give you a positive number for your mass, which makes sense. You get 1.5 kilograms. Mass is a scalar quantity. It should always be positive. Same with like time. So the math should work out. You should get a negative divided by a negative to make it a positive number for your mass. And that is the answer there. And that is the answer for part A. Okay, number 10. Switching gears a little bit, it's a graph type of question. It says a constant, unbalanced force is applied to an object for a period of time. Which graph best represents the acceleration of the object as a function of elapsed time? Interesting. So they're looking for the acceleration over a certain amount of time, and the only information they really tell you is that it's a constant, unbalanced force. Unbalanced force. So we could make that like one underline. See, there's two ideas here. There's an unbalanced force acting on it. You know from Newton's second law that if there's an unbalanced force, it must be accelerating. Also, they're telling you that this unbalanced force is constant. It remains the same the whole time. So if we look at the relationship for Newton's second law, the relationship between acceleration and the net force is a direct relationship. If the force is remaining the same, the acceleration must also be remaining the same. The force isn't changing, so it's not going to cause this to accelerate any more or any less. So we're looking for a constant acceleration because this net force is constant. And that would be choice D. Well, they're not lettered, but it's the last choice. Very interesting. I mean, you might have thought that the acceleration should increase somehow. But what is actually increasing? If you're accelerating, that means that your velocity might be increasing. Let's assume that the force is being applied in the same direction as your velocity. So let's make this velocity of time. Remember, what does the slope of a velocity time graph represent? Well, it's the change in y over change in x. So it's the change in velocity over time. The slope is equal to the acceleration. Now, we have a constant acceleration, so we should have a constant slope. This is showing a constant unbalanced force on a velocity time graph. Maybe you thought it should look something like this. Or maybe you thought it should look exponential like this one. Well, that would actually be what the displacement time graph looks like. And remember, the slope, M stands for slope in this case, not mass. The slope is equal to the rise over the run, the displacement divided by the time. So the slope is the velocity in a displacement time graph, and the velocity is increasing at a constant rate. So we want a slope that is increasing. So we want exponential curve. Wow, that was really bad. Something like this. Oh man, that's even worse. You get the point. It's exponential. It looks like this. You might have thought it was this one. That's the displacement time graph for this situation. You might have even thought it was choice A. That would be the velocity time graph. If it's a constant net force, it's a constant acceleration. Kind of tricky. You have to really know the concept here. Number 11, and then we're done. It says a net force of 10 newtons. Net force is 10 newtons. Accelerates an object at 5 meters per second squared. Okay. What net force would be required to accelerate the same object at 1 meters per second squared? So now what net force would cause this object to accelerate at 1 meters per second squared? There's two different ways to tackle these types of problems. One is with a lot of math, and one is kind of conceptual. So the first way I'll explain is with a lot of math. You could first figure out, okay, what is the mass of this object? That would be helpful to know, because if I know what the mass is, I could use Newton's second law to figure out what the force is. So the mass, let's say the net force is equal to the mass times the acceleration. 10 is equal to the mass times 5. so the mass must equal 2 kilograms. And you're accelerating the same object, so that means the mass is the same. And you just want to know, okay, if 10 newtons makes it go at 5 meters per second squared, how much force would be required to make it go at 1 meters per second squared? And do the net force is equal to the mass times the acceleration. The net force is equal to 2 times 1. So you get 2 newtons. 2 newtons of force, of net force, would make this object accelerate at 1 meters per second squared. I mean, that's a pretty decent way to do it. It's a little bit like I have to calculate things twice. This is more of a conceptual type of problem if you really are comfortable with Newton's second law. Let's look at the relationship again. So the acceleration is equal to the net force divided by the mass. Now, what did we do? We're taking the acceleration, 5 meters per second squared, and we're making it 1/5 as large. We're making it 1/5 as large. So we're going something like that. Or you could think of it as, dividing this by 5. But I think of it as like a fraction. It's 1/5 as big. Well, whatever you do to one side of the equation, you have to do to the other side of the equation. Since we're keeping the mass the same, it's the same object, we must make the force, the net force, 1/5 as big, because it's a direct relationship. So to figure out what force it would be, you just do 1/5 of your original force. So the original acceleration was 5, 1/5 of 5 is 1, the original net force is 10, 1/5 of 10 is 2 newtons. So you end up getting the same answer in 2 different ways. There's 2 different ways to think about it. Choice is up to you, but I highly recommend thinking of the relationship between the 2 physical properties that you're talking about. All right, thank you for watching, and have a nice day.